All right, so exams on Monday, right? And then our online one is Monday through Wednesday. Let's quiet down, please. And the second one will be Wednesday through Friday. Okay? Remember that we have homework due on Monday before the exam. We have all of the Learn Smart chapters are all due before the exam. And we have one more review session, which will be this afternoon at 4:30 to 6:30. Okay, in Widso 007. Okay, so you can hit that. All right, so we really don't have much left in chapter 19. All we're going to do is use a few slides to look at a couple of related acids. Not ones that we're going to do a lot of chemistry on, but they're important. Well, sometimes they're important in the chemistry we'll see. Sometimes they're important in biology. All right? And then after that, I've just came up with a few problems that we can go over just as a little bit of review for the exam on Monday. All right? Any questions before we start that? All right. Here we are. Okay, so the first two types of acids we're going to look at. The first top type are called sulphonic acids. And they should remind you of another strong acid that you've seen a lot before. What would that be? It looks very like sulfuric acid, right? So sulfuric acid has a structure just like this. Right? And so in sulfonic acids, we've essentially removed one of those OH groups and just added an alkyl group or a benzene group or some organic piece there. We know how to make sulfonic acids, benzene sulfonic acids, right? So how do we do that? Yeah, it's just a sulfonation reaction that we learned already. Okay? So when we look at sulfonic acids, the pKa's of sulfonic acids, where should I write this in here? Is somewhere around -7. Okay, so it's very acidic. So why is this sulfonic acid so acidic? Resonance. Exactly right. So if we draw out the conjugate base, we get this, right? We could have plus H plus up here. And we essentially have, we've got the sulfur in the middle, and because sulfur is in the third row of the periodic table, it can have this expanded, can go beyond the octet. And so it's kind of like, if you look at the structure as far as resonance, it's kind of like this carboxylic acid on steroids or something, right? It has even more resonance. So we can draw the resonance like this. We can take a pair of these electrons on this oxygen. We can donate them in and then push the electrons up onto another oxygen. And if we do that, we get the O minus up there. This, and we could do it again, right? And so essentially we're spreading that minus charge and those electrons over all three of the oxygens. Okay, so this makes for a very stable conjugate base. Therefore, the acid is very strong. Yeah?
Question. So with the conjugate base here, is there only two possible resonance structures, or would there be three?
Well, there would be three possibles, right? Because we can take these electrons and push it up onto the other oxygen. Right, so our third would be like this. Right, so what we're showing, even though, we really can't tell the oxygens apart, but we would essentially have a 1/3 minus charge on each of those oxygens. Okay, so that makes for a very stable situation. So we can have, it could be a methyl group on there, it'd be methane sulfonic acid. Common one also is with a trifluoromethyl, it's called trifluoromethane sulfonic acid, something called triflate. But other common ones, well, there's two up there. A very common one that we see is this para-toluene sulfonic acid. And we times abbreviate this with a TS, so tosic acid. So we've seen this kind of group before, right? What was that? How did, what?
Hydration.
In the hydration, right? We could use tosic acid just as an acid catalyst, right? What if we if we replace that OH with a chlorine? What can we use it for? Well, we can react it with an alcohol, right, to make a sulfonic ester. And what were sulfonic esters good for? They're good leaving groups. Okay, so making a sulfonic ester, so the ester would be if we have OR over there, and essentially this conjugate base would be the leaving group, right? And it's such a stable conjugate base, it would make it a very good leaving group as well. So it's another way to make an alcohol into a good leaving group. Okay? All right, so yeah, we can see these as leaving groups, and with this tosic acid, it's often a common acid catalyst. Okay? The other type of acid are the phosphoric acid esters. And so phosphoric acid would just have 3 OHs on it. So this is an ester because it has an OR right here. So this one has 2 OHs, so it has 2 pKa's. It can deliver 2 acids, or 2 protons, right? So if it delivers the first one, we could have 1 O minus and an OH. pKa of this, well, I guess of the acid on the left, I should put it over there. The pKa of this is about 2.35. Not really about, that's pretty precise there. But it can also donate another proton, right? And so then we would get this dianion. So what do you think for this second step? Is the pKa going to be lower or higher than the first step? It's going to be higher because we start to build up more and more minus charge on the molecule, and so that conjugate base, the second conjugate base over here, this one is less stable than the one in the middle, right? So always when we have diacids or polyacids, the pKa's go up as we go along. And so the pKa of this one is 6.9. All right, so considering these pKa's then, which of these 3 forms would we have if we had, what form at, say, pH equals 7.5? Which one? The one clear on the right. Okay, because we see, remember, whenever we have these, if the peak H is higher than the pKa, it will be in its basic form. Okay? And we know that pH is above 2.35, so that one's going to be ionized. It's also above 6.9, and so we're going to shift all the way over to this side here. Okay? Now, phosphoric acid esters are really important in biology. Okay? And the ones that are often important is the reaction between, well, we could have either one here, this monoester and a diester. Okay? Or, well, it's one of these. Actually, what happens is this phosphate group can go on and off of alcohols. And Dr. Henge, if some of you had him for class last semester, he studies this process of cleaving phosphate esters. And in biology, proteins are oftentimes, their reactivity is controlled by either adding or removing phosphate esters. So it's kind of like an activity switch sometimes. You put on the phosphate ester, it makes it active. Take it off, it deactivates it. And it's how the biological system controls the activity of its catalysts. All right, so it's kind of an interesting area of regulation in biological systems. All right, so the other type of, spend a little bit more time talking about at the end of this class, and these are the alpha amino acids. Okay, so amino acids are the building blocks of proteins, and so it's kind of a monomer, and we string them together into essentially a polymer. And there's 20 common amino acids, and they differ in what this R group is right here. So there's 20 different R groups. Simplest is just an H. We can have alkyl chains, we can have carboxylic acids, we can have aromatic groups, we can have a whole bunch of different groups on there. So that's how they're all different. How they're all the same is that they have this amino group. And remember, if we look at the position adjacent to the carboxylic acid, we can call this the alpha position. And so the amino group is attached to the alpha position, so it's called an alpha amino acid. So they all have at least one amine and one carboxylic acid. Okay? So if we have this amino acid, what do you think is going to happen if we just dissolve this in water? Is it just going to stay the same? No, what's going to happen to it? Right, so let's say, right, so if we think about this structure, right, we have a basic group on one end, and we have an acidic group on the other end, right? So it's like we're adding an acid and base together. So what kind of a reaction would we get? An acid-base reaction, okay? So the common form of an amino acid is in its conjugate acid of the amine and its conjugate base of the carboxylic acid. Okay, so it's this di-ion. We call it a Zwitter ion. Okay, so it's overall neutral, but we have a charge on the nitrogen and a charge on the oxygen. Okay? So for different amino acids, the point at which they become neutral like this can be at slightly different pHs. All right? And it depends also if this R group would have an acidic or basic group on it as well. Okay? But the effect of ionization based upon, pH is just like what we've been talking about already. Example here, this is alanine, all right? And alanine has its R group as just a methyl group, okay? All of the amino acids except for the simplest one, where instead of a methyl we would have an H, which is called glycine. All of the amino acids are chiral. Okay? So, here's our chiral center right there. So, is that chiral center R or is it S? You guys remember how to do that? Maybe. We got a 50-50. Huh? S? All right, so let's work it out here. So what would be the highest priority group? The nitrogen, right? What's second? The carboxylic acid. Third is the methyl group. Fourth is the hydrogen. Right, so if we just follow the rotation from 1 to 2 to 3 and back to 1, it's going clockwise, but because number 4 is out in front, right, we go clockwise, it would be counterclockwise if we looked at it from the other side, so it would be S. All right, so all of the common amino acids in proteins are S. Okay? Though they don't often in biochemistry, they do things weird, and instead of calling it S, they call it L. All right? Biochemists are behind the times. All right, so what is going to happen? So this is this isn't even the zwitterion, right? So this form of alanine, would this be present if the solution was very acidic or basic? Acidic, right? So this is the most acidic form, right? And I wrote this because it has both of the groups as acids, and so we consider what the pKa's of the two groups would be. Okay, we have a carboxylic acid. Remember the pKa of acetic acid is 4.8. All right, so look at this carboxylic acid here. Do you think the pKa would be the same, 4.8, or would it be lower, or would it be higher than 4.8? How many people think it would just be the same? Nobody? Can't commit to that? How many people think it would be lower? All right. How many people think it would be higher? Nobody. Lower. We're democratic in this class, right? Which I say whenever you guys get it right. So why is it lower then? So the pKa is pKa of the acid is 2.35. Right? So that's quite a bit lower than 4.8. So why is it lower in this case? Well, so we'd be considering the conjugate base, right? We want to think about the stability of the conjugate base. Is there any more resonance than usual for this carboxylic acid? No, not really, right? So what else could affect this? Huh? Yeah, so it would be an inductive effect, right? We saw already, we didn't talk about it too much, but it was in our table that this type of ammonium ion, if we put it on a benzene ring, it's a strong deactivating group, right? It has that full plus. And so essentially, that ammonium ion can pull electron density away, right? Which is an inductive effect. Stabilizes the conjugate base, makes that carboxylic acid more acidic than if we just had acetic acid. Okay? The pKa of the ammonium ion is 9.87. Okay? So let's just consider, so if we wanted to generate this form, this ion, in this form right here, what type of pH would we need to have? Huh? Yeah, this one right here. How low? Right, lower than 2.35. Right? Because if we want that carboxylic acid to be in its acidic form, we need to have the pKa below, or the pH below its pKa. right? And if we want to have all of it in that form, we probably have to go another pKa unit or more below that. Yeah.
So just to clarify, the carboxylic acids pKa is 2.35?
Right, that's, yeah. Wrote it right next to the carboxylic acid, right? Just to clarify. All right, so what if we had... So this form, we would have at a pH less than 2.35. Okay? What about if we had a pH of 7? What would the ionization state be? Okay, what about the amine? Would it be protonated or deprotonated? Okay, let's look. It's pH. The pH is 7. Is that above or below the pKa? Below the pKa. So if the pH is below the pKa, should that be in its acidic form or basic form? Acidic form. All right? For the amine, right? That has the pKa of 9.87. The pH is below 9.87. Right? It's at 7, right? It's not below 2.35 yet. Right. So we would have the ammonium ion here. What about the carboxylic acid? Would it be in its acidic form or basic form? In its basic form. Okay, so here we have the Zwitter ion. All right, what if we have the pH, let's say, equal to 11?
So we'll have the amine in its basic form.
What would its ionization state be?
Should be both should be in the basic form.
CH3. Okay, what about the nitrogen? All right, so now the pH is above the pKa, so it's going to be in its basic form. So how many hydrogens should I put on there? 2, right? So it's going to be just the neutral amine. What about the carboxylic acid? Basic form as well, so it's going to be the carboxylate anion. All right, so by varying the pH, we can go between 3 different ionization states. All right, if we have 2 acidic or basic groups. Yeah, question.
So aside from being the average of the pKa's of the 2 groups, what's the point of an isoelectric point?
Okay, so here, just a minute. Let me introduce it first. Other than that, so each amino acid has something that's called the isoelectric point. Okay, and that is where the pH at which the amino acid would be neutral. Okay, and the way that we calculate it is just by averaging the pKa's of all the acidic and basic groups in the structure. Okay, so for alanine, we would add the pKa of the acid, 2.35, plus the pKa of the ammonium ion, 9.87. We divide that by 2. We get a PI, or an isoelectric point, 6.11. Okay, so each amino acid is going to have a slightly different isoelectric point. And especially if you have a group here that has, say, a carboxylic acid on it, right, we would be averaging in another pKa for a carboxylic acid. Okay? So that would lower the isoelectric point. So one of the important things about the isoelectric point is that amino acids can be separated using a technique called gel electrophoresis. And you essentially put a voltage across this gel, and the amino acids will travel towards the negative side or the positive side based upon their ionization state, and that ionization state is dependent upon the pH. Okay? And so they will, if the isoelectric point is slightly higher or lower, will affect which direction they go, toward the negative or the positive pole, or how fast they move. Okay, so it's just a property of an amino acid. Okay, any questions? Yeah.
So is the isoelectric point sort of spectrum? Because at 6.11 it's obviously neutral, but it's also neutral at 7.
Yeah, right. So the question is, right, this is a whole range. It's all acid-base chemistry. Right, so it goes back to that, what was that equation called? The Henderson-Hasselhoff, right? Right, and so that told us what the concentrations of the acids and conjugate bases would be at different pHs. All right, so we know, so we said at pH 7, we're going to have this ionization state. But we're actually above the isoelectric point. So that means that we might have slightly more of one of the ionization states than the other. We're not exactly the 1-to-1 position, right? So we're going to have as we go over the continuum of the pH, we're going to have slightly different populations of the different ionization states, right? It's just all in equilibrium. Okay? Any questions? Any more? All right, so that's everything I have for you for this chapter. All right, and so my idea was just to maybe, we don't have too much time, but look at a couple of different problems. Okay? So I'm just going to kind of throw slides for them. But I just wanted to do a few, partly to remind ourselves of where we've come during this time since the first exam. Okay, so let's just start out with a simple system like this. Okay, so we just have a alkene that is conjugated to a benzene ring. Okay? And we're just going to first look at a electrophilic addition reaction. We're just going to add HBr to this. Okay? And so let's figure out what the product would be. All right, so we have two possible products. Right? So is the HBr going to go on, is the bromine going to go onto the benzene ring? No, right? So we can't do electrophilic addition reactions on benzene rings. Right? Why can't we do addition reactions? Right, because it breaks up the aromatic ring. It's no longer aromatic. That's very unstable, so it's going way up in energy. Right, so we have two possibilities. We're going to add an H to one side of that double bond, bromine to the other side. So we could either add the bromine to this side and an H to the other side. I'm not going to draw the H in. Or we could end up with the bromine at this position. Okay, one of those products is much more favored than the other, right? So which one is more favored, the left or the right? Right. How many people think the left structure? Okay, how many people think the right one? I heard somebody say right. Democracy. Yeah. So of course, since we voted for this, the left one is the major product. Okay, so why is that? Yeah.
Because it forms a carbocation at the benzoic position, which is way more stable.
Exactly right. So when we protonate this, right, we generate a carbocation, and we want to generate the most stable carbocation. Or it wants to, or it does. It doesn't really want anything. It's just a molecule. So we protonate out here, we generate the benzylic carbocation, we've drawn all the resonance structures before, right? And so this is the most stable one. We add bromide, or bromide's already in there, that reacts at that position. Okay? So it's just all about the most stable carbocation. All right, so let's do this one. And let's add HBr to this. Okay, and we'll consider, both low and high temperatures, right? But let's consider all the possibilities first. All right, so the first thing we need to do is figure out where this diene is going to be protonated to form the most stable carbocation. Well, this one's a little tricky, but probably on the left. So the first thing is that we have 4 positions that we could protonate at, right? But I gave you a general rule that we're going to rule out 2 of those, right? So which 2 do we rule out? The middle ones. And why is that? Because if we protonate at one of the middle positions, we end up with an isolated carbocation. Right? If we protonate on one of the ends, we generate an allylic carbocation. Right? So we generate a carbocation that has resonance, and so that makes it more stable. So we really only have 2 possibilities. And so we are going to protonate it. This may not be the best. I can give you a tricky example here, which isn't so good right before the exam. All right, so we're going to protonate on this end here. And this is probably what you would want to do anyway. So we're going to protonate there. We get a tertiary carbocation, which has resonance. Like this. Okay, so why am I talking to myself and saying this is a tricky one? Yeah.
Because if you protonate on the other side, you still get resonance over both secondaries and the tertiary.
Right. So it's kind of trying to decide whether a cation is spread between a tertiary and a primary position. Allylic carbocation is better than spread between a secondary and a secondary one. Right. Okay. So that's probably cutting it a little close. I won't cut it that close in the exam, I promise. If I happen to ask a question like this. Okay, so let's say we're going to say the tertiary is really the most stable, so we're going to generate the carbocation that includes the tertiary position. All right, so then in our second step, bromide can react with either end of this allylic carbocation. All right, so it can react at this end to give us, I'm going to put these both up on this side, so this product, or it can react with the other end of the allylic carbocation. Remember, these are not 2 separate carbocations, right? They're just the resonance contributors, right? The real carbocation has the charge spread between those 2 positions. All right, and so this would form, this with the bromine over here. Okay, so let's say that we do this under cold conditions. All right, so would that be thermodynamic or kinetically controlled? kinetically controlled. So which of the two products should be the major product? The one on the left, right? And why is that? Right, because this is the 1,2 addition. And we said that the 1,2 addition always forms faster because of something called the proximity effect. Right, we protonate, and then bromide is just right there, so it reacts faster to the end of the carbocation that's closer. So this is the 1,2 addition product, and so this would be the major product if it's cold. Okay, it's formed faster. Now, if we did this under warm conditions, so this would be thermodynamic control, which of the two products would be formed as the major product? The one on the right. And how do we determine that? Because it's more substituted. The more substituted alkene is more stable. Right, we could call this a tri-substituted alkene. It has 3 carbons attached to the alkene. Where this, what would we call this one? It just has 1 carbon attached. We call it a monosubstitute. Okay? So, under warm conditions, this one would be formed over here. This is the 1,4 addition. Okay? This is thermodynamic control. This one is kinetic control. Okay? So, do we always have to get, so is the thermodynamic product always the 1,4 addition product? No, it doesn't have to be, right? We went through some examples where it wasn't. All right, so we always know, well, so it's always, the stages, we have to decide which is the most stable carbocation. The 1,2 and 1,4 will always come from the same, from the most stable allylic carbocation. Right? We don't protonate at one position to do the 1,2 and protonate at a different position to get to the 1,4. Okay, we generate one most stable carbocation, and from that allylic carbocation we can generate the 1,2 and the 1,4 products. Okay? All right. So, any questions on that? Yeah.
Why didn't we protonate at the other position?
Why, what?
Why didn't we protonate at the other end?
Because I decided that we were going to say that having this tertiary carbocation is going to make, as a contributor here, was going to make the biggest contribution to stability. Okay, even though we said it, they might be close. Okay, and that's just the example I chose. All right. Asking how we might convert, or how we might make this molecule right here from benzene.
And then we would do like reduce them,
Okay.
right? So we do like 2 nitration reactions and then add the.
Okay, everybody have an idea out there? Okay, so if we start with benzene, all right, so let's go retrosynthetic here. So what's going to be the last step that we have to do to get to that product?
Reduction.
The reduction, right? And what are we going to reduce? What groups? Right? There's going to be 2 nitro groups, and we're going to reduce both of them. So we're going to have a nitro group here and a nitro group over here. Okay? And how can we do that? That one, the Wolff-Kishner is for the ketones,
So H2 and D.
right? So we can use hydrogen and palladium on carbon, or the other one that we listed was tin and hydrochloric acid. Yeah.
No, iron and hydrochloric acid also work, right?
Yeah, I think iron was in the textbook too. Yeah. In fact, or iron and hydrochloric acid. You want one more thing to pack in. All right, so then what would be the next step that you would do before that? Adding the bromine, right? And how can we tell that we're going to get the bromine at the position we want it to be at? Right, because both of the nitro groups are meta directors. Meta and meta, so this one is going to its meta position. This one is also going to the meta position. So the bromine should end up, right there. Everything's working together. Okay, so the reaction conditions, we just use bromine and iron 3 bromide. Okay? And then from here, I think I'd rather have us show this in 2 steps, since we have 2 groups. All right? And so we can add 1 nitro group on. Oops, let's put this one on. Leave that one. Okay. And because this group, like above, is meta-directing, right? If we do that nitration, we'll get the second nitro group meta to the first, right? How do I know it's not going to go over here? The same thing, right? Yeah. Okay, so this is just nitric acid with sulfuric acid as the catalyst, right? And then we can go all the way back to benzene, same reaction. Okay? All right. So don't forget about the review session today at 4:30 with SO007. And I have made all of the assignments up to this week, so you can go in. If you go into Connect, you can find them under, they say the same thing, but it says practice. So if you want to go back and redo any of those, there's lots of questions in there to draw from. So it's a good way to study as well.